So in this video, we're going to talk about inferential statistics. So if we measure a small sample from a large population, we can determine the statistics for a larger population using this small sample. Okay? So if we have an n number of measurements, we can calculate some statistics. So notice that we'll have our average, we'll calculate the same way we did for a large population, but our variance, instead of being using sigma squared x, we'll use S of x. So S of x is for a smaller sample. Alright, again, the formula is still the same. Alright, and then we'll have a statistical degree of freedom is a new term v. Alright, and that is going to be equal to the number of samples we took minus 1. Alright, for the finite number of samples, we can define our probability of our mean value using this equation here, where x bar is our mean value, and then we can use our what's called our t-score to multiply by our standard deviation to determine that percent probability. So our t-score we can define as using the following equation here, right, where we take the mean value of our data set, we subtract x prime from it, and then we divide that by our standard deviation and divide that again by our square root of n. So we can look up our t value once we know it in the table on the right hand side here for the number of our whatchamacallit, our standard, if we know the number of degrees of freedom, we can look up our t for the desired probability that we're interested in. Okay, so so please notice is that the number of data points you take will affect the shape of the curve that you get. Okay, so if you had enough time to take an infinite amount of data points, it would converge towards a normal distribution. But for smaller data sets, the bell curve is much flatter than it is for the continuous. Okay. All right. So in addition to that, there's another thing that we need to be interested in, which is called the standard deviation of the means. So if we take multiple samples, so we take a few different types of data sets. So we have m data sets, all right, with each of them having n measurements. Okay, so each of the curves would look different, right? So they would each have their own mean value. They would each have their own standard deviations. It would be a mess. So in order to kind of determine a representative data set for the entire population, we need to determine what is the standard deviation of these means. Okay, so so what we can do is we can say the standard deviation of the mean would be equal to the standard deviation divided by the square root of n. Alright, so the likely range that the true mean value falls within a certain range, we can say again is going to be equal to x prime plus e is equal to x bar plus or minus, again, the t-score times sx bar. So notice the only difference between the two equations is ss bar, which is just a little bit smaller than the previous term. Okay. All right. So we're going to do an example problem soon where we'll consider the table, the data in the table on the right-hand side, which we used a little earlier, and we're going to estimate the interval of values which 95% of the measurements should be expected to lie. All right. So we'll do that in Excel. So we're going to do that in the next video. All right. All right. And then the last thing is that you can pool your data together using the following equation. So if you took you had m data sets, each of n measurements, all right, you can pool these data sets together using these variables. So you can do a pooled mean, variance, standard deviation, pooled standard deviation of the means, and then you can do like things like the pooled mean squared value, all sorts of things. All right. Not super critical for this class, and I'm not expecting you to be a master in statistics, but these are the procedures that you would have to use.